start with hierarchical independence. Hierarchical independence. Hierarchical independence. So what do I mean by hierarchical independence? What do I mean by hierarchical independence? So the hierarchical independence. The image, so let me start, in fact, by considering this simple model, even though the proof I will give not for the model, but directly in my situation. Okay, so let me start with explaining what my situation looks like. I already said this during last time, but now let me be a little bit more precise. Okay, so we start with finite branched tree. With finite branched tree. With finite branch tree, and in each vertex of the tree we put a random variable. So let's say normal random variable in each branch of the tree, and then we consider the sum of the random variables along the branches. We consider the sum of the random variables along the branches. So we sum along the branches. These sums, so for example, it can also be like this. So these sums are not obviously independent. At the same time, the sums after, so there are two paths. They have a common part and then they diverge. They have a common part and then they diverge. So after they diverge, they become, in fact, independent. They become, in fact, independent. So, I claim that, for example, if I put large deviations, if I'm interested in the maximum value, so let's say maximum value of Sn, and I'm interested in the logarithm, then the logarithm of the maximum value of Sn would be exactly the same as if they were independent. So the growth of the logarithm of the maximum value of Sn, so we can try to evaluate this. In fact, let us be extremely naive. So I have sum of n Gaussian random variables, so the variance is n. The variance is n. The number of the sums is 2 to the power n. The number of the sums is 2 to the power n. So it is clear that, considering that the variance is n, so I can go, well, we have to solve the equation 2 to the power n times e to the minus c squared over 2n to n is equal to 1. So if it is less than 1, so please remember again that I'm only interested in the logarithm, I'm not interested in the next term. It would be very interesting, by the way, to start the next term. So if it is C is bigger than that, then the probability is exponentially small. If C is bigger than that, then the probability becomes exponentially small. So from here, the maximum is seen to be, one can see, excuse me, from here, I have C roughly equal there is something I'm not doing right. No, I think no, this is correct. So C is roughly equal square root of 2 log 2n. So, and in fact, this is the right order of the answer. This is the right order of the answer. So this is the right order of the answer. The right order of the answer. In fact, so the maximum. So anyway, excuse me. The maximum over Sn over this quantity excuse me, the maximum of Sn over n is this quantity. So the fact that it grows, that it is bigger than this plus epsilon goes to 0 exponentially. This explains. Goes to 0 exponentially. Goes to 0 exponentially. Please forget the logarithm I wrote here. It was a misprint. No, there is no logarithm. This is like this. So the confusion, excuse me, the confusion is that there are two. There are two variables. There are 2 to the n, the number of variables, and there is also the depth of the tree. So this is one has to be very careful about notation. But the way it is written, it is correct. The interesting point is that the probability of max Sn over n is less than this minus epsilon also goes to 0. So this is the interesting point. This is the interesting point. In fact, so okay, so the probability that this maximum is less than 2 log 2 minus epsilon goes to 0. Goes to 0. So in fact, again, if I have, let us recall again, so I just multiply, I don't care for sub-exponential terms. So I have 2 to the n variable times e to the minus, well, obviously c square n square over 2n. I don't care about 2 square root, I don't care about this at this time. So clearly, if c is small, this sum of probability is exponentially large. So it seems reasonable that at least some event should happen. And in fact, if I had independent random variables, then clearly the probability that neither of these events would happen, would be on the order of 1 minus e to the minus clearly c squared n to the power 2 to the n. So, and again, this would be very, very small. This would be super exponentially small if they were independent. So if the random variables were independent, then both of these estimates, this estimate is just very naive, and this estimate is, and this estimate follows from inverse Borel-Cantelli lemma. So this is the key point. Obviously, Borel-Cantelli lemma is true always, but inverse Borel-Cantelli lemma is not always true. So excuse me for saying such naive things. So the point is precisely that this hierarchical structure, while not being independence, is still sufficient to have the same estimate. And in fact, very elementary argument can be given for this, which is due to Nicola Kistler. So let me give it in let me do it the following way. I will give it in very vague way. I will not give details, but then when I consider my situation, which is similar to the situation, and in fact also similarity of study of characteristic polynomials of unitary matrices, with this model it's observed by Argand, Delis, and Bourgache. So, and I use it in situation for sign process, Argand, Delis, and Bourgache, and I use it for sign process. So then I will give the details. So right now, let me give very intuitive arguments, So in fact, following Kistler, so what does Kistler do? It's interesting argument. So Kistler uses Paley-Zygmunt inequality. So it's essentially inverted Mercalli lemma, but from technical standpoint, it's Paley-Zygmunt inequality. Let us recall that for z positive random variable, the Paley-Zygmunt inequality says that the probability that z is bigger than theta expected value of z is at least 1 minus theta squared e to the z squared e to the z squared. So in fact, the Paley-Zygmunt inequality says that precisely if the square of the variable is comparable to the expectation, to the square of the expectation, if the expectation of the square is comparable to the square of the expectation, then this is because random variable is not too small. It cannot be too small. If it's too small, then such situation is not possible. If it's too small, then if it's very probably too small, then in order to reach the expectation, it must be somewhere too large, and then the expectation of the square will be significantly bigger than the square of the expectation. This is the idea behind the Paley-Zygmunt inequality, and we can see that the proof is two lines using Cauchy-Bunyakovsky-Schwarz inequality. So the point is that in order to estimate the probability that something is big, one simply needs to have upper estimates on the expectation of the square. One needs to have upper estimates on the expectation of the square. Upper estimates on the expectation of the square. Okay, so, but to have upper estimates on the expectation of the square, so let's see, to have upper estimates on the expectation of the square, so precisely I need to have upper estimates here. So I need to have estimate of the event that, for example, I have two paths, Sn1 and one other path, Sn2. And I need to estimate the probability that this one is big and this one is big. So if they were independent, I would have product and end of story. They're not independent, so they have a common part. So in fact, and this is the formalism developed by Kistler, it is also possible to do it in a different way. The result itself is not due to Kistler, it's just different approach, which is very robust, because in fact Kistler uses very little. This is the whole point. Okay, so the approach developed by Kistler is just summation over the common part. So the common part and, well, obviously the independent parts, and the simple remark is that the common part, the probability that the common part is big is obviously exponentially small. So the common part is with overwhelming probability very small. And then there is some summation of logarithmic scale, and this is how the argument of Kistler works. And again, I hope towards the end of the talk today to do rigorous version in my situation. Just what I want to say is that this is the picture that is behind what I'm doing. So let me, after this preamble, let me do a little reminder of what I'm doing. So I'm doing the sums for under the sign process. So I'm investigating. the additive functionals, the additive sum functionals under the sign process. So I consider the sum of values over functional. And I'm interested in showing, so what is at the end of the game, what I'm going to obtain at the end of the game. At the end of the game, I want to show that the asymptotic characteristic polynomial, so this random entire function associated to the sign process. So this random entire function, my aim is to show that this function is sufficiently big, sufficiently often. So I will show that the probability, of such acts that the measure of T, the Lebesgue measure of the set of T, such that Gx of T is bigger than T squared. So T is taken in interval between T and 2T. So there is big number T. There is big number T, and there is this, okay, so this is bigger than T squared, T small squared. I can also write T large squared because at this point it's the same. That this Lebesgue measure is bigger than some T to the power delta. Yes. And this probability I will show, the probability of this set is bigger than some epsilon. And this is all I need. This is all I need because, again, let me recall that what I'm proving that this Gx divided by one linear multiple, so divided by this very T squared, fails to be square integrable. But in fact, I show that it fails to be square integrable by showing that it fails to be square integrable by showing that it is on the order of constant for large moments of time. I should also say that just as in the example which I gave, I can show this for also bigger values of T for bigger exponents. So this square, which I wrote here, let me write again, T squared. So I show T squared, but in fact, I can put any number instead of square, I can put any number less than 2 square root of 2. Less than 2 square root of 2. It's exactly, please remember that I had square root of 2 log 2 in the example before, but it is because I had binary tree. And here, so to speak, this log 2 disappears. So there is, because a binary tree, the variance grows like n, and here it grows like log t, sure, log 2 disappears. So it becomes 2 square root of 2. 2 square root of 2. Okay, so I can write any power, any exponent less than 2 square root of 2, and then the probability will be like this. So this is enough for me. Also, let me say, equal to the delta, and of course there is another. So let me just say that, by the way, also that of course once I have shown that the probability is bigger than some constant, then by 0,1 law, it's possible to say that in fact it's also equal to 1. So let me just say it very briefly, once I have shown that it's bigger than a constant, bigger than a positive constant, then I have also shown that it's on the order of 1. Okay. So now the argument which follows the pattern of Kistler and Argan-Beres-Bourgade just is cut into the following steps. So first of all, as we discussed last time, I have this analog of Seagal's theorem, so this very precise statement about exponential moments. Let me write alpha because it's also common. So I have this integral of f plus alpha squared over 2 square of the Sobolev 1/2 norm, where C of alpha is some function which does not exceed. It's an entire function. It's an entire function. F is supposed to be in the Sobolev H1/2 class. Is an entire function which does not exceed some constant. So H1 norm over pi alpha and H exponential of H infinity norm. So this is my key estimate. This is my key estimate, which implies, by the way, also C of alpha is less than 1 for alpha in R. So my random variables are sub-norm. My random variables are sub-norm. So this estimate, in fact, by playing with it, and especially taking into account this Sobolev H1 norm. So I already explained that my game, the name of the game is that H1/2 norm stays constant and H1 norm goes down. This is the name of it. This is what you might say, but how is it possible that Sobolev 1/2 norm is constant and Sobolev 1 norm goes down? But in fact, it's possible because I am interested in low frequencies, and please observe that I'm writing not norms but semi-norms. So let us write them again just one last time. So Sobolev 1/2 semi-norm is the integral absolute value of lambda f lambda, whereas Sobolev H1 norm is of course integral lambda squared f a. And of course, it is absolutely possible, especially when we're interested in low frequencies, which is what we're interested in, especially when we have functions supported in whose Fourier transform is supported around 0. It is very possible that H1/2 norm will be big, while H1 norm is small. And this is exactly what happens. Please observe again, I say norm, but I mean semi-norms. I'm writing semi-norms. I'm interested in semi-norms. Okay, so this gives me normal approximation for my additive functions. Normal approximation for my additive functions. Normal approximation. But I need more. I need more. Here I would like to explain the key step. The key step that I need. The key step that I need. I need not just normal approximation. I also need independence, and please observe that here, so this should informally be thought as exponential of Gaussian random variable, okay. So, well, the fact that exponential is bigger than something, it means that the Gaussian random variable is also bigger than something. Bigger than what? Gaussian variable bigger than what? Bigger than its variance. One can compute. So again, let us observe that I'm interested in the situation when the function f is just f of t, is just something like logarithm t minus logarithm of t. So this quantity is not, as we discussed last time, this function is does not belong to the Sobolev 1/2 class, but in fact we consider a cut in frequency space. We consider a cut in frequency space. So I take Fourier transform. Then I cut frequencies from T inverse to 1. And then I take inverse Fourier transform. So just I'm cutting frequencies from T inverse to 1. I am not interested in anything else. So please observe that this function, the variance, so the variance that's only 1/2 norm, will become log t. One can compute it without difference. It will become log t. So I'm interested in the situation when Gaussian random variable is on the order of its variance. This probability is, of course, small. The probability of Gaussian random variable to be on the order of its variance is small. But also, it's important to keep in mind that I'm also interested in independence of such events for different values of the shift, because this is exactly what I want. This is exactly what I want for different values of the shift. So, and this is the subtlest point. So I need not just Gaussian approximation, but Gaussian approximation quite far. So, and let me explain how I do this. This is the key point. This is the key point of the argument. Okay, so I erase the statement. I erase the norms. We don't need them, at least not right now. And let me go to something that everybody remembers from lectures in probability theory in university, just the Berry-Essen inequality. The Berry-Essen inequality. In fact, I will need not exactly Berry-Essen inequality, but some version. So this is precisely. So Berry-Essen inequality. I am considering the most naive version of the Berry-Essen inequality. So for identically distributed independent random variables, just the Berry-Essen inequality for independent random variables. So it says that the Kolmogorov-Smirnov distance. So I consider just sum of independent random variables over square root of n. Independent identically distributed random variables. Yes, over square root of n. Yes, that's good. So I'm interested in the Kolmogorov-Smirnov distance between this and, well, what it converges to, the standard Gaussian. The standard Gaussian. And in fact, this distance, so let us recall that Kolmogorov-Smirnov distance is just the maximum of the differences of distribution functions. So this is Sn. So Sn minus distribution function of the normal distribution. So this maximum is just the Kolmogorov-Smirnov distance. Well, I should maybe write supremum in the case that this one has 8 and it's okay, whatever. So this is the Kolmogorov-Smirnov distance between these distributions, between Sn and the normal. And so the Berry-Essen inequality, I'm not interested here in optimal constants. I'm only interested in saying that the Berry-Essen inequality says that the Kolmogorov-Smirnov distance between Sn and the normal distribution is constant over square root of n. Constant over square root of n. How is the Berry-Essen inequality proved? The Berry-Essen inequality proved with help of formula, which is also often called Berry-Essen inequality, which is just the, in fact, the estimate of Kolmogorov-Smirnov distance in terms of characteristic functions, and it is written usually like this. So phi1 and phi2 are the corresponding characteristic functions. So then this is the integral. This integral as such usually diverges. And so one needs to, it suffices, as observed by Berry-Essen, to take the integral from minus t to t. Then there is a constant which I do not remember. And then there is a correction term c2 over t. And then there is a whole game of optimizing these constants C1 and C2. There are many works, including by the Russian school. So there is a very beautiful paper of Stеклова from the 60s, where she also treats the case of random vectors, and there are some developments recent and so on, but just the point is that, of course, taking t to be square root of n and not thinking very much and just having naive estimates for the, so if I'm not interested in the constant, then this is naive, this naive argument is just sort of exercise you can do for exam in probability theory. But my point here is that this Berry-Essen inequality does not give any information, for tails, So I am interested here in, so let me explain. I'm interested here in situation when I'm interested in a situation that this random variable be on the order, well, here I have divided or not dividing, by the way, doesn't make a difference for combinatorial distance. So so I have divided, so I'm interested for this random variable. Excuse me, I take it back. So excuse me, I take it back. So, so of course, for the distance, it doesn't make a difference, but for what I'm about to say, it does make a difference. So I'm interested in situation. So let me not divide. So you will see why. You will see why it is important for me. So let me consider the not divided random variable. So I do not normalize. So now I would have obviously random variable, sum of independent random variables of total variance n, and obviously the standard Gaussian of total variance n. And I'm interested in the probability of this random variable, this random variable, being on the order of the variance, that is to say n. Being on the order of the variance, that is to say n. But such probability is e to the power minus n. Is exponentially small. So the Berry-Essen estimate, it doesn't give me anything. I want to say that the probability that this random variable is large is comparable to the probability that this quantity, of the same probability for this quantity. And this is exactly where Berry-Essen inequality doesn't give me anything. But it would give me, so now comes the key point. Imagine, so now I write modification of the Berry-Essen. By the way, I should say, I'm absolutely sure that this modification must have been considered in the literature, probably by Berry and Essen themselves, but so I will be very grateful for a reference. So for a precise reference. So modification of the Berry-Essen. So let me consider this integral, but not on real axis, but on shift of the real axis. So we need some assumption that exponential moments exist, and so let's make assumption that everything exists. So I have phi 1 theta plus I lambda minus phi 2 theta plus I lambda. over lambda theta plus I lambda, of course. D lambda. Fantastic. 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 So this is sort of integral I get. Again, let me not go. So this is kind of integral I need to test. And if I'm interested in probabilities that, difference of probabilities that my one random variable is bigger, so let's say psi1. Psi1 is bigger than some t minus psi, minus probability that psi2 is bigger than some t. Then this is just this. Maybe I need to take some averaging, but let's just write it like this, in this very naive way. Oh, this is perfect. This is absolutely perfect. There is, of course, also e to the I lambda, e to the I lambda t. But it will disappear in absolute values. Okay, so now I take absolute values. And let us imagine that for some reason I know that this quantity is dominated. So let me write e to the minus theta t. That this quantity is dominated, that growth in terms of theta is at most normal. So let's think that sigma is the variance of sigma square is the variance of psi1 and variance of psi2. In fact, it will not be exactly true in our situation, but okay, but let's just make this. Again, I'm just giving first caricature of the argument, and then I will give it. Then this is e to the theta squared sigma square over 2. And then the resulting integral, assuming that I'm able to match the derivatives here, the resulting integral will be convergent integral. Which will give to me contribution sigma square. Which will give to me contribution sigma square, because there is one sigma coming from here and one sigma coming from here. So the difference becomes sigma square. But this probability, again, considering now you can see that t must be chosen in such a way so everything has to match. T has to be chosen as precisely theta sigma. Yes, exactly. So everything matches. So this becomes e to the minus sigma square theta square over 2 over sigma square. And precisely, please observe that in view of this argument, this very naive modification of the very lesson argument, I am able, so please understand, I am not estimating, I'm not giving better estimate on Kolmogorov-Smirnov distance, no. But I am saying that the estimate, the difference in probability, so let me put it in a different way. I'm estimating not just the difference between probabilities, but in fact, you can see, because the error term is less than either of the terms, I can divide by it. I am estimating Radon-Nikodym derivative. I am claiming that Radon-Nikodym derivative of my distribution with respect to normal distribution is close to constant. It's close to constant. Very far away, all the way to the variance rather than the square root of the variance. And this is the key point. So Kolmogorov-Smirnov distance may be quite large, but the point is that the distribution stays similar to the normal distribution all the way very high, all the way to very small probabilities. And this is the point of, and this can be done again by simply shifting the contour of the integration. And again, I'm absolutely sure that this remark was made in the 40s or at some point, and I would be very grateful for a reference. So now, let me just say one more thing. And here I'm coming to the key point, and maybe here I will just say the idea and skip technical details and refer you to the paper. So the key point is that in order to carry through this argument, I need an estimate not only for low frequencies, but also for high frequencies. And for high frequencies, please observe that this estimate is simply not good enough, because this quantity explodes. So to carry through the modification of the very essence argument, I need the following estimate. So why do I need it? I needed to ensure convergence of the integral. I need the following estimate. So I erase the very essence argument because I don't need it anymore. I need the following estimate for high frequencies. High frequencies of vector functions. And so the high frequency of vector functionals, so the statement is the following. Theta plus I lambda is less or equal than exponential. Well, theta square over 2, clearly f h1 half squared. So the subnormal term minus, and this is the key point, minus some gamma absolute value of lambda times this very f h1 squared. Well, I write the term precisely, but these are just technical details that you can ignore. Just plus. So here I want to put plus d. And here I put gamma squared lambda squared f h1 squared plus some d. Let us note, I just write a statement, it's a little bit long, but the key point is this. And really, this is a very naive statement. Because the statement is just the following, excuse me, it's a very naive statement. Its statement is just the following. So for some of independent random variables, the the characteristic function, excuse me, let me note here, for some of independent random variables, the characteristic function has exponential decay. it seems very clear. If I go a little bit far away from 0, then of course, under normal circumstances, my characteristic function is distinct from 1. And so then when I take the sum, it has exponential decay. This is more or less what is happening here. This is more or less what is happening here. So there are all sorts of correction terms and so on, but the key point is just this, that the characteristic function has exponential decay in lambda. Has exponential decay in lambda in this very precise sense, where we do not forget that this is quite precisely the variance. This is quite precisely the variance. Okay, so now the only thing that also in the little time that I have that remains for me to explain. So let me say how this argument is obtained. Unfortunately, I'm not able to explain in this course. This requires, let me just say that this is the key point, and here the argument requires a change of variable argument. It's in the spirit of Kurt Johansson, and just this is from technical standpoint, this is the key point. So I need to introduce change of variable argument and essentially to replace fast oscillating integral by, well, as happens in change of variable, replace fast oscillating integral in by exponentially convergent integral. And the key technical point in this, let me just say very, very briefly, the key technical point in this is that the group of diffeomorphisms acts on the sign process. Group of diffeomorphisms acts on the sign process. Group of diffeomorphisms acts on the sign process, and it let's say diffeomorphisms of compact support. So this is something like De Finetti theorem. This is something like De Finetti theorem. So what does De Finetti theorem say? De Finetti theorem says that measures invariant under group of permutations are Bernoulli measures. So sign process is not invariant under group of, so instead of group of permutation, we have diffeomorphisms. Of course, point process invariant under group of diffeomorphisms is Poisson process. So sign process is not, of course, invariant under group of diffeomorphisms. It is, however, quasi-invariant. So, and this is precisely the point. So the sign, in order to do change of variables, I need to study the Radon-Nikodym derivative of the sign process under group of diffeomorphism, and this Radon-Nikodym derivative can be written explicitly, and this is the key technical point of the paper. So let me just write this and not say anything else, because this would require separate discussion. Just this is the Radon-Nikodym derivative, and this is the Radon-Nikodym derivative. Yes, and just it is necessary in order to obtain deformation of the contour. When I deform the contour, obviously I need to study the change of my measure under deformation of the contour and develop this result. Okay, and in the remaining very few minutes, let me just say what I promised in the beginning. Let me conclude the argument for hierarchical independence. So I erase all of this because I will assume this, and let me just go back to the setup of the last lecture. So I take, okay, let me erase. So I take my function, as we discussed last time. I take my function. So f0 of t is the inverse Fourier transform. So I consider my sums f. So fn of t is f0 of t to the power n. I'm interested in the sums of the form. I'm interested in the sums of the form f0 of t plus large plus f1 of t plus t large plus fn of t plus t large. Then there is one sum of this form. So this is precisely the expression for the logarithm of this function by cutting all the frequencies which are too high or too low. So I cut, so you can see that by doing this, I go in the frequency space up to r to the minus n, and frequencies above 1 I just cut. They don't make a difference. So these are the expression I want to study, and these are precise. Oh, excuse me, why did I raise this? So excuse me, I keep this. So I have this one, and I have same one for different moment of time. So, and these become independent. So, well, they're not exactly independent, but they are sufficiently dependent. Please allow me to skip the technical details here. So, the independence is controlled by this estimate. They become sufficiently independent. So, f, in fact, I can write precise statement. So, fk t plus t1 plus and so on. Excuse me, f0 plus f0 plus fk. So for different indices, they're independent because frequencies are disjoint. T plus t1. Actually, let me write just here. So here up to k, if instead of up to n I write up to k, then these are independent, are essentially dependent, provided t1 minus t2 bigger than r to the k. Well, you can see here that if in fact fk t plus t1, for example, is equal to f0 t plus t1 over r to the k. So it makes a lot of sense that independence occurs when the difference is bigger than r to the k. Okay, so now comes the key step, the hierarchical independence, and with this we close for today. So just they we consider, following Kistler, we consider this sum. So let's see, f0, f1, and so on, fn, shifted sum, f0 t plus t. So first of all, we cut. Here we cut into some big pieces, m big pieces. So I sum not from f0 to 1, but from 0 to fm, fm plus 1 to f2m, and so on. M big pieces. Why I need this, and you will see right in one minute. Then, and this is the key, it's very simple, but it's also very somehow astucieux. So the argument is I cut away, I throw away the last piece. The last piece I throw away. I don't care for it. I throw it away. Okay. Now comes the key point. I want to estimate. So I want to estimate. Please allow me not to introduce a lot of notation, otherwise it will be not possible. I want to estimate the probability. I want to estimate the probability that each of the m pieces is big. How big? I already said this, on the order of the variance. Please observe that since these pieces are essentially dependent, the variance is summing up. So I claim, I estimate the probability that each of the m pieces is on the order of the variance. Each of the m pieces is big. At time t1 and at time t2. Well, here we have to estimate separately the pieces which are bigger than this and the pieces which are not bigger than this. And so the estimate becomes, there is a quantity for the probability of the pieces, rho 0. So, to what power? The power of, well, m minus 1 for the first piece, product, m minus 1. And for the second piece, I only consider those parts where they are not far enough, plus L minus 1. Where, what does it mean, L minus 1? L is precisely this number. I did not make it, it's not bad. And now I just need to consider, so, and here I conclude, I just need to consider the sum in the Taylor-Zygmunt inequality. I need to consider the sum over all L. So I have T whole number of times, rho 0 m minus 1 plus L minus 1. And then I observe that the number, please observe, I'm summing over couples, T1 and T2. So this L is large if this L is large if T1 and T2 are sufficiently close. So they're sufficiently close. I have to divide by T. I have to multiply by T to the L to the M. I'm summing over couples. So this is the key point. So it's just summation of geometric series. Please observe. I'm summing over couples T1 and T2. So T1 is chosen in T ways. T2, on the other hand, is chosen in function of L. L is the length of the coinciding piece. L is the length of the coinciding piece. L is the length of the coinciding piece. So the number of times that it can be chosen, if coinciding pieces of length L, then the number of choices is T to the power L over M, because these are the coinciding pieces. So, and you can see that this is less than, that in fact, the piece for L equals 1 dominates everything. So this is less than T to the rho 0 m minus 1 squared. Which is precisely what? Which is precisely the square of the expectation. Well, there are some constants lying around later. So which is precisely the square of the expectation. So because, again, the first term, what I mean the first term? The first term is, excuse me, the first term is the term for L equal M. I say the first term, in fact, this is maybe what is confusing. So the first term, I mean the mth term. The term is, excuse me, the term which dominates is the term when L is equal to M. That is to say, when T1 and T2 are sufficiently distant, well, it makes sense that if I choose a pair T1, T2, then the dominating attribution is when the distance between T1 and T2 is on the order of T. So, but this is precisely what is written. T to the power rho 0 m minus 1 to the square. And the other terms are smaller by factor T 1 over m. Well, clearly rho 0. So you can see T minus 1 over m, rho 0, and this is less than 1. So this is the key point. Please observe inverse. Yes, well, exactly. This is what it is. Please observe that precisely for this argument to function, I needed to cut these last frequencies. If I didn't have these minus ones, the argument would not have functioned. diamond would not have functioned. So I needed to cut these frequencies because, well, in fact, because even if I diverge at distance t, there is not enough independence to ensure the how to say, the decoupling of these lowest frequencies. So I have to stop here, so to speak, one step above. So this extremely naive, you can say, but also very smart argument of Kistler precisely allows me to use the Peele-Zygmund inequality using the estimates which have been so far cancelled. So the key estimates on the characteristic functions. I can prove I can use the Peele-Zygmund inequality. I can estimate that the inequality that was written here, that the number of times when these quantities are all large grows as t to the gamma, which means that this function divided by t squared fails to be square integrable, which is exactly what was the aim to prove, which was exactly the point, the main theorem that we were proving here. Thank you so very much.
Just to be sure, you wrote C of alpha. It is simply the...
Can you say again? Can you say again?
C of alpha. When you wrote about the characteristic function.
Yes, yes, C of alpha, yes?
Yes, yes. Is it simply Levy's part of his representation?
Can you say again? It is simply what?
The Levy's part of his representation. Like the integral of e to the power I alpha x minus 1. The integral part of the Levy's representation.
I'm not sure. Let's discuss separately because I'm not sure I understand what you mean.
Ну, давайте я по-русски додам. Это просто часть экспонента Леви, правильно ведь? Ну, то есть там был альфа интеграл, это сдвиг, потом был альфа квадрат пополам, это гауссовская часть.
Ну да.
Вот, ну то есть имеется в виду, что просто распределение является безгранично делимым и...
Нет, это я не утверждаю. Нет, я думаю, что нет.
Это не так. Это не
нет,
так.
это я не утверждаю. Может быть, оно приближается. Нет, это я не утверждаю.
Угу, понятно.
Нет. Думаю, что нет. Этого я не утверждаю.
Но при этом она задается как бы ряд.
Нет, а почему? Нет, извините меня, может быть, простите, пожалуйста, может быть, я не совсем, может быть, тут, я пишу, нет, извините, пожалуйста, я пишу. Нет, это интересный вопрос, давайте обсудим, потому что, на самом деле, это интересный вопрос, и тут для меня есть некоторая неясность. Значит, я пишу, что мое распределение является, является c альфа на e в степени, ну давайте без этих там, давайте просто альфа квадрат пополам на вот это число, норма. Но я хочу обратить ваше внимание, что никто не сказал, что c от альфа это там функция распределения, это специальный момент функции распределения. Например, вот этот SF может иметь атомы. Это ничему не противоречит. Моя случайная величина может иметь атом. Ну и что? Это ничему не противоречит.
То есть нас интересует только оценка.
У нас есть, ну не то, что нас интересует, у нас есть только оценка.
Да.
То есть, по-видимому, ответ на ваш вопрос, если я правильно понял ваш вопрос, ответа на него нет.
Да, я понял. Спасибо большое.
Да, so excuse us for the Russian discussion, Javier. So the answer is no. So this random variable, it's possible for it to have atoms, in fact. So it's just, I have estimated that C of alpha is less than, well, whatever, this double exponential, but end of story. So there is just no, it is not, so it is not exponential moment of random variable.
Mm-hmm.
So what was the answer to his question on the integral? It was that wasn't what the
answer to this question was no.
Okay.
At least it seems to me no, because again, this random variable, it might have delta part. It might have atom. It is possible for it to have atom. So if function f is compactly supported, if you think about it, it's even intuitively, even in finite dimension, it doesn't matter, infinite dimension, even in finite dimension, if function f is compactly supported, so let's look at definition, I erased it. SF is just sum over particles, yes? So if function f is completely supported, then it is possible that there are just no particles in support of f. So then this function is equal to 0 and it's positive probability. So it has atom, but it doesn't contradict this representation. The function 1 over the function e to the minus alpha squared certainly satisfies this inequality, right? So there is no contradiction. Vina, does it make sense what I say?
Just 1 second. Yes, I understand what you're talking about. However, let's assume that X is the Poisson field. Then and F also.
The Poisson field does not satisfy this. Poisson field does not satisfy this. Poisson field does not satisfy this, if I'm not mistaken.
Yes, obviously not this equality.
Right. Okay. Yes, excuse me, please continue. Yes.
I mean, for instance, F has the compact support, then it also has an atom, even if X is the Poisson field. However,
that's exactly right. Yes, yes, yes.
However, it should be infinity divisible.
But yes, okay.
Why everything ruins in this situation?
But because for Poisson you have independence, and here no.
Yeah. Well, okay.
Yes, because for Poisson you have independence, and here precisely this is, in fact, you ask a very good question, because this is exactly what I did not have time to discuss. So negative, in fact, this plays a very important role in proof of the other estimate, that there are negative correlations. The particles push each other away. So it's not independent, it's negatively correlated. The particles repel each other.
Mm-hmm. Thank you very much.
Does it make sense?
Yes. Now,
okay. Yes, thank you very much. Yes.